Good afternoon, everyone. My name is Shiva. My name is fairly long, so we'll keep it quite fairly short so you can all remember it. And this is my esteemed colleague, Dr. Jorge Candiotti. We're here today to present about robotic wheelchairs. How do we define them? And to give you a general idea of where we're at. Okay. So we'll just get the conflicts of interest out of the way. Jorge and I are one of the two inventors for our robotic wheelchair that you see here to the right. And the contents of this paper don't reflect the views of the Department of Veteran Affairs or the United States government, as we're both VA employees. Okay, learning objectives. So what I want to sort of get across is how do we even define a robotic wheelchair, the concepts of how to create a robotic wheelchair, how do we know how ready it is, how do we classify it? And we'll give you an example of our project here to the right of those kind of step-by-steps and how it's been illustrated. So the reason why I got into this whole thing is as I started my master's and PhD, I was trying to look through literature of, well, how do you create it? You know, what is the exact definition of it? What's kind of out there? And is there a standard, for example? I know there is for power wheelchairs, but what's there for emerging technology like this? And that's where I couldn't really find anything. So I set out to write this paper to sort of define it, classify it, and create a taxonomy, which we'll show you here today. So I just wanted to get an understanding from you all here. What would you consider a robotic wheelchair? Just wanted to get your thoughts and ideas around this. What would you consider to be one? Yeah, anyway, it's an open poll. I wanted to sort of engage with you guys.
Actually, it's
Yeah, that's good.
just to start, I want to know, maybe I want to know more about the audience. So I just want you to ask, when you raise your hand, how many of you are engineers? Okay, good. How many of you are clinicians? Okay, so it's half of half. So, I mean, you guys have experience with wheelchair users, with power wheelchairs. So I think that's the whole idea of this project, right? Is try to provide improve the technology for this for the wheelchair users. So yeah, like my colleague Shiva was saying that we wanted to know what is the definition for you? What is the definition of a robot, and how is that applied to a wheelchair? So ideas.
So I guess for me, since we're trying to define this apart from just power wheelchair, the power wheelchair is just used to go in the direction. I guess robotic would be any additional mechanical function that is provided.
Yeah.
Like somewhat intelligent.
Right.
Yeah.
The intelligent system, right? Intelligent wheelchairs, like yeah. Oh yeah. So yeah, so we were asking, what is the for you guys? What is the what do you define a robotic wheelchair? How would you define it as, right? So you say an intelligent wheelchair, a device that can sense the environment. Any other questions? Any other suggestions for a robotic wheelchair? Mechanical transformation. Right, transformation, degrees of freedom, right? Range of motion.
Yeah.
Good.
Anything? All right. Okay. So yeah, we're pretty much all on the right line. So ideally, so how I set to define it is essentially a robotic wheelchair is a power wheelchair, plus the ability to sense, plan, and negotiate throughout environments through indoors and outdoor settings. And I want to really stress this through indoors and outdoors. As we're all from this space, we're so common to sort of hear that, you know, wheelchairs are only meant to be used for indoor use only. But how I want to be able to sort of define it and go forth from this, that robotic wheelchairs are meant to be used for indoors and outdoors. Stairs are not limited to only just homes and indoor spaces. One step, you know, just having one step into your home is not, you're not only limited to that. outdoors, curbs. So that's the reason why. So that's why we actually have this taxonomy. So instead of trying to reinvent the wheel, what I try to do is see what's kind of already out there in terms of standards and sort of mesh it together. So this robotic taxonomy is broken down into sort of two core components here. You have the wheelchair standards as outlined by ISOs and Resna. And then you've also got mobile robot standards as well. And I'll go into these. So the wheelchair standards, especially as it's to be an indoor and outdoor use, we want to make sure that the mass of the wheelchair, the static and dynamic stability are all compliant with existing standards. Now we know that a sort of as functions do develop, more advanced functions develop with these newer wheelchairs that we see in research and that are commercially available, that standards will need to adapt to this, and there will need to be a change. But for now, we wanted to make sure that first and foremost, it is a power wheelchair. And I also wanted to highlight power seat functions. Our users that are going to be using robotic wheelchairs are power wheelchair users, and power seat functions, as you all know, are really quite essential. So that's why I wanted to sort of put that there. And especially dimensions, you've got to be able to fit it in and out of your home, as you do with your or on public transportation. So yeah. And the next thing is mobile robot standards. So with this, there's sort of six features that I wanted to sort of go through. One of the main things is mobility. It's ability to navigate, go through terrains, obstacles, and then it can be you will have levels of automation that can be derived from it. And then you've got to factor in its level of AI, the human role, and also the robotic wheelchair's ability to interact with itself, with the user itself, and other technology, for example, other power wheelchairs, or other technologies that you would have in your home environment. And lastly, on this is the communication standpoint. Not everyone's able to use a standard joystick, for example. If there are power wheelchair users, there would be adaptive add-ons. And these are some of the core things that need to be factored in when you're developing a robotic wheelchair. So the input and output communication ability. So if I take this one example through mobility and how does that actually translate to levels of automation? Now, this is very, very similar to autonomous vehicles in terms of how it's already defined. So I haven't deviated too much from there, but I'll give you an example. For a set of tasks. So, for example, I am going to go from here to the Westin Hotel, and I'm encountering potholes. We in Pittsburgh know very well that we are not short of potholes. So when we're designing such, for example, for that specific task to go through potholes, we need to be able to say how critical is that task? How much is the robot accountable for that task? What level? So there's like a spectrum there. And also the last thing is the environmental complexity. Is it only meant for controlled conditions, especially as you're developing it in research? Is it able to go through outdoor conditions? And these things need to be defined. So if we take that task to be able to navigate through potholes, you need to be able to say, okay, how much can the wheelchair sense, plan, and negotiate? And that on that spectrum, you need to be able to say, how much on that scale can it is it capable of it doing? And that's how you actually are able to derive here if it's a conditional, how much conditional automation it has, or if it's fully automated. And that's how these levels 1 to 5 automation levels were born. So if I go through this, I've kind of spread it out on a sort of table here of each level of automation, and kind of sort of take you to a story. So if I take you to that example of going from here to the Westin Hotel with no automation, I'm completely driving on my own. You know, I'm not really having much assistance, not any assistance from the wheelchair. But then if you go to sort of level one automation, say, for example, there was an obstacle on the road, there was a lamppost. So if I accidentally sort of drive into a lamppost and it detects and stops that wheelchair, that's a level one automation. But if I take that automation up a level and say, okay, it's detecting that lamppost and it's able to avoid that lamppost, it's able to drive around it, that's another level of automation. And these can be described as user driving support features, just to help aid it for certain with certain level of automation. Now, if we take that one step further, we can now go into a lot more of an autonomous wheelchair where it's autonomous under certain conditions. And that means that it requires the user itself, such as myself, to interact with the robotic wheelchair less. So we're able to say that, okay, if I'm able to program the wheelchair to say, yeah, please take me to the Westin Hotel. And it's able to do it under certain conditions. Maybe it's only able to do it under a certain protocol. For example, not in all weather conditions or all environmental conditions. So we need to have that flexibility and be able to say, okay, where is it? Where is your robotic wheelchair on that spectrum? So I want to take this to you guys again. We want to try and find the balance between autonomy versus automation. And I wanted to gauge your opinion as an audience, as we have this kind of 50-50 balance of, you know, what do you guys think? Do all power wheelchair users need a fully autonomous wheelchair or not? So I just wanted to sort of gauge your opinion here for a couple of minutes. Any takers?
I'd ask the user. I pose that question right to the driver.
Yeah. And what circumstances would you see that?
What's that?
What circumstances? Have you seen any? So are you a clinician or an engineer?
I'm an ACP.
Okay, so have you seen any cases where autonomous wheelchairs would, robotic wheelchairs would be most beneficial? It's okay if you haven't. I just wanted to gauge your sort of experience of actually.
Yeah, especially control, visual impairment for your level one.
So it's very much dependent on your disability. Yeah. Anything else?
There was a study done by University of Chicago and with this particular problem. And it found very simple thing. People don't want to give up control.
Okay.
They have very little left, so they want to compete.
Yeah.
Powerless where you're 3D mapping someone's predetermined route, then it could be a lot easier for them at that point too. Then you make it full autonomy, right?
Right. So we want to give that user more control of, okay, to have the ability of having a fully autonomous wheelchair, but the user is able to say, okay, I want to be able to control up to this level, to be able to set it to, okay, it can only do certain conditions. Sometimes I may need it to do more.
Turn on and off, the option to switch.
Giving the user the autonomy to have that option.
Yeah. Things change.
Yeah.
We do that within different.
Please.
My first reaction was like, oh, that's scary, right?
Yeah.
So it's a great thing, but even just like a Tesla or a car that's going to be autonomous, there's always the safety issue that is kind of the first thing in my mind of like, what if something happens, or even like a visually impaired person, like there's always something in the environment that's going to jump in front of the chair, or maybe it goes off track and ends up in the middle of the street. Those are the kind of things I've mentioned that I'm listening to, you know, it sounds really scary.
And that's why this is why when it comes under sort of this levels of automation, it could be under specific conditions. It depends. You know, can it be under all conditions, under emergency scenarios? Is there protocols in place? Are there the standards set in place so that these are evaluated safely?
Kind of going off of that, also if and when some of these autonomous like automatic features fail, is there a reliance on from the driver on that certain automated feature? So if that's then removed, does it not just taking back to where they were before, but even further, like, less.
Right.
Right, so you're mentioning, what you mentioned before is, it's a little bit of education from the clinician and the user, right? There's some training process as well, to train on a device that is actually rather novel or new. So there's also different components when it comes to robotic wheelchairs or what we're trying to address, right? The other portion about the safety features as well, in case something wrong happens. I think that's what we're trying to address this in this robotic taxonomy, just to provide some guidelines, at least for the future or the upcoming devices like this. And then, yeah, so disability is definitely everybody, every user is different. Of course, we're not trying to make a one fit for all device, but at least I would at least try to create like a research platform or like a basic platform and then customize it to the end user, right?
Hence the taxonomy. We wanted to try and keep it as broad as possible so that when you're designing this robotic wheelchair in mind, you're able to cater it and design depending on the user's needs, or you're designing for a spectrum of users. And that's what we wanted to try and sort of hone in and sort of create. So the next thing is, how do we classify them? I've seen so far I've been going through a lot of papers and stuff, and I wanted to sort of, where are robotic wheelchairs on a spectrum? So I kind of had to look at from a clinical research sort of side of things, and then you've got the engineering component. So I needed to combine both worlds here if you're going to be able to do this. So we've got NIH's stages of intervention development. It's talking about efficacy testing, effectiveness testing, and then you've got the engineering side, from it being a research proof of concept to all the way to a commercial product. Where are we on this spectrum, whether it's in research or in the market? So that's why I did a sort of scoping review and looked through nearly 5,000 articles through all these databases, and I narrowed it down to this. So these are the kind of three main categories what I've kind of seen. You have commercial robotic wheelchairs that are out there in the market already. Then you have adapted designs. Now, what I mean by adapted designs is wheelchairs such as myself, my own power wheelchair, people have put sensors on there to be able to do certain things. And that's when a majority of the research that I've seen out there that's been published. Now, and then you have a few that are like novel designs where people have designed something from scratch. So if I take the commercial robotic wheelchair space, we've seen advanced features such as obstacle detection, stair climbing, attitude control. But challenges is that so far there's some basic sort of partial automation level. And then in terms of research, there's been some pilot testing that we've seen out there with a few actual real users. And at least on the engineering side, they're operational as a commercial product. And the next thing is with this adaptive designs. So a lot of what we've seen out there in research is just basic science. And if there are any testing, a majority of them have been just testing with able-bodied users out there. And that's not very telling. And so far, a lot of them have been sort of validated in the lab. And it's a real struggle. And we know that, it's not easy as like, yep, we've developed something, we can put it out there in the market. There's steps to it, and it's expensive. But that's what I'm trying to sort of get across, is that's what's kind of out there already. And the last thing is novel devices, especially such as this chair. So again, we've seen some sort of basic science approach and some sort of partial user testing with actual real power wheelchair users. But they're still very much in development, trying to get something designed from scratch into a commercial product is quite a laborious task. and quite costly. And that needs to be facilitated in here. And that's why I just sort of looked at the spectrum of what's already out there in this research and got to this. Now, the next thing is Jorge here is going to talk you through how we've kind of sort of followed this step so far and just show you where we're at from our perspective. Good.
Yeah, so we wanted to present an example of how we use the robotic taxonomy as on our robotic wheelchair. So you are, well, most of you are familiar with this design process. So we actually do a participatory design process, right? So we bring all the stakeholders, the end users, the clinicians, the engineers, and we have a focus group where we actually ask them what are their users, what are their needs in terms of at least of mobility and safety. So then after we gather all their needs, we create our proof of concept. This is our initial meeple design. We bring them back to see whether the capabilities of meeple actually meets their users' needs. And once we actually get that validation, we go further into developing the applications and test it in controlled conditions and without the user. And then once we prove the safety of the device, we test actually with wheelchair users just to understand the feasibility of the device, how it is used, about the ease of use of the device and so on, right? So once we prove this, we also use the technology readiness levels, right? We want to make sure that it meets the basic needs, also meets the safety through the ISO standards. And the goal of this is to translate it from the research into the market, right? So again, this is the robotic wheelchair taxonomy. We use the wheelchair standards, the ISO 17176, and also some of the mobile robot standards as well that Shiva just mentioned. So following these participatory designs, from the user's needs perspectives, what we gather is that we wanted to address the comfort from the seating system, but also from the mobility portion of the wheelchair. We wanted to address also the safety when driving over uneven terrains or challenging environments, and also the accessibility, for example, when you're driving on the sidewalk or trying to access the sidewalk, but the curb cuts are blocked. There's no way to go over the sidewalk except for driving on the road. So following this robotic wheelchair taxonomy, we first wanted to meet the wheelchair standards. This already is pretty established. We use the ISO standards 7176 in terms of seating and mobility. In terms of robotic mobility standards, we also wanted to address the level of automation of the applications that we're going to show. Also, other thing I wanted to mention is in terms of the communication of the interface, like how the user and the robot communicate with each other in order to tackle these environments. So at this point, this is our first version. This is something that we actually showed back in the ISS 2019. So what we had here is like meeple has different range of motions. Everything is just, all the changes that you see here is pretty much in the base. The seating system is similar to any off-the-shelf device that you see out there. And we just focus on the base. The base is it's able to move the wheels up and down. It has articulated legs. So you can provide the seating functions, not just in the seat, but also in the base. It also has the option to move the wheels back and forth. So you can change the maneuvering to either front, rear, or wheel drive motion. You combine all these features, the user is able to maintain the seat level on inclined surfaces, and also is able to go up the step, at least one step at a time, of 8 inches. So I want you to keep this in mind, that the user is able to perform these applications, but they have to manually be controlled, right? What you see here in the slide here, this is the interface that they were using, where you can control each arm or each wheel manually. So like I said, in the participatory design, it's a long word. So in the participatory design, we brought back these wheelchair users. What we gathered, we showed the applications demonstration. And what we gathered is that the people were likely to use the self-leveling application and also be able to climb curves. And the other one that we also showed was that they would like to have traction control, like when driving outside of the environment, outside of the house. The next thing that once we validated this, we wanted to evaluate the usability and also the safety of the device. So we first focused we've evaluated the engineering, through engineering tools. For example, we want to make sure that the MiBot met the ISO wheelchair standards. Also, we also tested with a dummy or in this case, also one of the researchers as well. Yeah, that's normal. I mean, research. Just to make sure they safe and reliable before testing with the actual end users. Right?
On the dummy.
Students are expendable. So the next thing, though, we also tested, once we actually meet this and we didn't kill anyone, we actually used the usability evaluation, right? We wanted to test it with experienced wheelchair users. So we recruited wheelchair users, tested MiBot on these different environments, and then we wanted to get their feedback, their perspective on how easy it is to use and what else we can improve on the device. And also, just to a note on this, we want to actually use standardized measurement tools in order to test the effectiveness, efficiency, and satisfaction. So like what you see in the slides, we tested on 3 particular parts of the ISO standards: the static stability, dynamic stability, and the dimensions, right? You guys want to make sure that we also want to see what are the limitations of the device in terms of range of motion and stability. The next thing is that we recruited participants. The questions that we wanted to add, the research question was actually, how easy does MiBot operate, or how easy do wheelchair users operate on challenging environments with MiBot compared to their own chair? So we recruited 10 participants, 10 wheelchair users, and we asked them to drive MiBot and their own chair in these environments that you see in the slide. It represents indoor, outdoor environments, but also environmental barriers like curbs, cross slopes, and curb cuts. What we saw in the results is that MiBot was able to complete more tasks than their own chair, particularly in the environmental barriers. Also, when we asked them using the Quest tool, how satisfied are you with the device with MiBot versus their own chair? The results were the same, which actually the results are actually good in a good way, because with the minimum training, they still like to use MiBot compared to their own chair. One of the issues or limitations that we saw though in the study though is that whenever they try to go over the curb or the cross slope, like I mentioned before, they use the interface where just use one wheel at a time. Even though they were able to complete the task, they show a high mental demand, effort, and even frustration when going over these environments. And for this, they use the NASA TLX, if you guys are familiar with it. Actually, raise your hand if you know what the TLX is. All right, only a few. All right, that's not good for me. So yeah, so the NASA TLX is called the task load demand. So it measures clearly how mental effort does the user perform. It requires to perform a task in this and based on the device. All right. So based on the feedback that we got, we make a few changes. So that's the new version that we have right now. It still has the same range of motion and degrees of freedom, but what we particularly changed was on the interface. We focus on going from the manual version into a more automated version. So you actually reduce the task load or the NASA TLX scores. All right, so what you see here in the features, what was performed manually, now is performed automatically. Let me just show you a video here. In this case, this is called the curb climbing application. So instead of using this manually, controlled manually, the only thing that they have to do is just to line up to the wheel, to the curb, and then press a button. Once you press the button, then the chair just automatically do these functions in order to climb over the curbs. This process takes around 30 seconds. Something I didn't show here is that manually version, it takes around 2 minutes and a half. So yes, and okay, you have any questions so far? No? Okay. This is something, this is another, yeah. So this is another application that we work on, actually that Shiva actually work on this application. We're trying to make it more autonomous. The idea is to actually detect the curb using a stereo camera, stereo vision camera, in order to detect the curb automatically, and then the chair will alert the user whether they want to go over the curb or not, just to have like a confirmation from the user. And if the user decides to do that, then the chair will they will take control over the process, and this doesn't work. But that's the whole idea, though. That you detect the curb, and then the chair will automatically try to go over the curb.
And the reason why we started to actually do that is because we had some user feedback of just being able to just align to the curb. Some users found it a little bit difficult, a little bit cumbersome. So that's why we started to do this automated curb recognition, so that as they drive up, all they have to do is just click a button and it will be done for them. So, yeah.
Okay. Right. So one of the questions that we had is like that goes back to the robotic taxonomy, robotic wheelchair taxonomy. Is how much automation do you actually want in your wheelchair? How much automation does the wheelchair user wants when they performing this kind of application? So the results show we compared the automation versus the manually version using again the NASA TLX. And what we saw here is that it's kind of obvious results, but still we wanted to quantify these results though, is that, okay. Oh, I was looking at the pointer here, but looking at this. So what we saw here is that the users that prefer the automated version, they score a lower mental demand, mental effort, way less frustration, and higher performance. So even though this is almost obvious to use an automated version for this type of application, we still wanted to quantify this. The interesting thing that we found out though is from anecdotal results is that half of the participants still wanted to be in control of the device, right? So even though you just press the automated version is just press a button and let the chair do it. But some others actually prefer to be in control by either pausing or stopping the chair in case something wrong happens. Right, so it's like a half-half. It goes back to, it depends on the disability, depends on how much perception the user has to control the device. Now, the next application that we have here is the self-leveling application. So because most of us is ATPs, practitioners, engineers, what happens here is that we have an IMU sensor in the wheelchair. So it's able to detect the ground, the angle of the ground. And once it detects a change, what the chair does is automatically maintain the seat level to compensate for the change in the surface. So we tested it in control environment. We also tested in this other environment that simulates incline surfaces, what is called the Karen system. Just to make sure that it's safe and reliable and test at a dynamic stability, but in a controlled environment. So, okay. Now, another question that we had is, how do you quantify safety when driving on these environments? Typically, you measure this, maybe you can do it two ways. One is to ask the user's perception, right? The other one is to actually measure safety. You can measure safety based on the context. So in this case, we wanted to measure safety by measuring the seat inclinations, the changes in the seat angles of the chair. So in this case, what we did is we compared the first version of MeBot, the new version, and their own share in these 3 different environments. 10 wheelchair users drove over these environments. And what we found out is that whenever driving over these environments, wheelchair users experience a really high seat change in their own wheelchair, on their own power wheelchair. That's because obviously it doesn't have this dynamic stability compared to MeBot. But what it was interesting to see is that when driving over around 10 degrees of change, 10-degree slope, you can actually see a even higher angle of almost up to 30 degrees. And why is that? Is because sometimes wheelchair users actually have their the seat tilted already when driving over these environments. What I wanted to point in here is that MeBot still shows some seat changes, but it wasn't as much as compared to their own device. The other thing that I wanted to point out here, though, is that between both MeBots, though, I want to see the difference between in the design improvements. And what we saw here is on the second MeBot, the new one, it shows less. It was more consistent in terms of motion control compared to the previous version, because the previous version used pneumatics. That's what I'm trying to point out. The last thing also we wanted to reiterate the usability of MeBot. How easy it is to use this device compared to their own chair and the previous design. So the main things I wanted to show here, point out is that in terms of usability, just to mention here is that we use the system usability scale. This is a standardized tool. And again, I wanna ask, raise your hands, who knows the SUS tool? All right, a few researchers from the lab. Okay, great. Yeah, so what I wanted to point out is that this is a standardized tool. What we found out is that we asked them how frequent will you use this device, and they said that they will agree to use this device very frequently compared to their own chair. You also show more consistency compared to the previous version as well. And it was very easy to use as well as their own chair. So it was really good to see that with minimum training, it only took 15 minutes to train the wheelchair user on use the sub-leveling device, the sub-leveling application. So it was good to show that MeBot and their own chair, they have the same response. Some limitations, though. Limitations is that we tested in the control environments, unfortunately. Well, we actually tested in purpose in control environments because we want to test the safety and reliability in these environments. So the next step is actually to test in real world environments, have more of a long-term study as well. The other issue or limitation that we had is the sample size. Only 10 wheelchair users. For those who do research, sometimes it's difficult to find this population in your region or in your where close to where you work. The other thing, though, is that I wanted to make a note here is about the using a subjective outcome measures, because it depends very greatly on the user's perception. It depends on the day, depends on the different factors. Sometimes it can go, it can vary a lot. Sometimes also depending on the tools, it can just reach a ceiling effect as well. So it's always going to be high. So what I want to measure here is that it's always good to complement this data with actually with quantitative tools, so like data from the sensors. And the last thing is that we tested with their own, we compare with their own wheelchair as a gold standard. I mean, we already know that power wheelchairs are already able to, it provides mobility independency but unfortunately it's also limited to flat environments. And we wanted to address that MeBot was able to that when MeBot was able to go over curves and also slopes. We wanted to evaluate with more advanced power wheelchairs. So the goal of this is to maybe try to improve the devices so we can actually, or test it with devices that are more advanced, like what you see here in ISS.
And I think what we want to sort of strive forward is we want to incite sort of more innovation, more competition, because that's how we sort of all work together here and sort of help, everyone in this standpoint. So this is why we want to compare with other robotic wheelchairs that now come into this space instead of just their own power wheelchair.
Okay, so just so yeah, and the next steps for this is we actually want to move it from the research into more into the market, right? So we wanted to move from the readiness level 5, like that's what MIWIT is right now, into a readiness level 9 to use it in real world environments, test it with end users, have a more long-term studies as well. The other thing that I wanted to point out is that just goes back to what we were mentioning is that the level of automation will depend also on the user's impairments and users' needs. And last thing is that with the robotic wheelchair taxonomy, these are just guidelines for the future designs. One of the things that we wanted to address though is to be able to quantify these standards like what we have currently in the ISO wheelchair standards.
So overall, I hope you sort of all kind of get an idea of how to sort of define a robotic wheelchair now, and understand the taxonomy. What are the core components that are involved in sort of building a robotic wheelchair, and sort of how to classify them. If you look at robotic wheelchairs that are out in the market, how much the research is like, where is it on a spectrum? How ready is it? Has it been tested with real world users? Has the efficacy testing been done? Effectiveness testing been done? Has it gone into clinics with real, OTs working with real patients? Has all these things been met and done? And this is what's not so clear out in the research sort of space, and that's why I've tried to sort of attempted to sort of evaluate that, to say, all right, let's gather what's been done so far and sort of put it on some sort of spectrum, so that when you take it on board, if you are working in this space at all, or eventually, and I'm hoping that robotic wheelchairs will come into the clinic, and eventually, here's me being hopeful. But if it does come into the clinic, it's just, you'll understand it. It's like, okay, the required testing has been done. It is commercially available. The engineering sort of ISO standards has been met. It's been clinically tested with a real world. It has met certain criteria. And this is how we want it to expand into standards now. This is that next step. We've got this kind of guidelines here of how to build it and how to create it and how to classify it. But now we need to implement that change more onto the standards now and get that in place. So, yeah.